This is P10T5. I'm Jim22303-708. The purpose of this simulation is to provide interactive sandbox for kids, allowing them to visually learn the relationship between explosive force and kinetic displacement through real-time experimentation. Let's start things off with a live demonstration. Upon launching the simulation, you'll be greeted with an instruction scene. On the right, there's an asset area, and on the left, there's a simulation area. Press E to start. Kids are able to place objects such as the car in the simulation. They are able to drive it with A, D, or arrow key. Kids are able to learn the interactions between objects such as crashing the car, and upon crashing the car, you'll no longer be able to control it. Kids are also able to learn the explosive displacement of objects, such as the example as seen. It reacts realistically. Pressing escape gives you the pause scene, and pressing number 2 gives you a preset scene. Pressing enter, you are able to see that the displacement of objects closer to the bomb is greater than those further away, thus distance plays a part. Kids are also able to learn angular forces, such as follow. You can see the car rotates, thus learning about angular forces and its relation and proportion to explosion. Kids are also able to learn properties such as when two forces are on opposing side, it causes it to stay still or go straight up. Kids are also able to learn, go crazy with the simulation, for it to be fun and interactive. And lastly, to show the scalability and extensibility of our abstract engine, we are able to still launch the demo video from part 1, thus showing it how it evolved from this to the simulation you have just seen earlier. And that is the end of the demonstration. Thank you.
I'm Isha, student ID 2502446.
Our primary focus in class ambition was maturing the abstract engine's type safety. Instead of using manual casting, we use Java generate and class tokens across the layers, hence eliminating runtime crashes. Specifically, in our create entity method, we pass the class token of the entity we want, which allows the engine to return the exact subtype and compile time. If the code compiles, the type is predicted to be correct. This will hand in hand with our abstract factory. The factory handles the heavy lifting, like composing a car's multi-chassis or a bomb-specific hitbox, while the engine remains entirely unaware of these concrete details. This decoupling ensures the engine stays at the universal platform where the simulation handles the complexity. To adhere to the solid principle, we apply the dependency evasion principle. Our entities never depend on the concrete manager. Instead, they interact via the iCreate entity interface, allowing entity to trigger its own response logic without being tied to a specific manager implementation. We prioritize the Leskov substitution principle by ensuring the same entity manager is fully backward compatible with the base engine. Whether it's at the manager level or the entity level, like substituting a bomb with a small bomb, the system handles the math analytically without ever needing to check the specific type. To certify this principle, we had to ensure our same entity manager wouldn't crash the engine while spawning entities during the physics calculation. We solved this by overriding the add methods using a different command pattern. By implementing an add queues list, we decoupled entity birth from the box 2D physics setup, hence allowing safe instantiation outside the box 2D simulation loop. In conclusion, the engine layer established the contracts through abstract interfaces. Our managers governs the lifecycle via deferred queues for system stability, and the simulation layer injects the concrete strategies that define our specific game logic.
Hi, I'm Sanrom 250331, and I'll be going through our movement system for part 2. Here are the improvements from part 1 submission. First, let's start off with share entity list. Get movable entity list build a new array list each call as a defensive copy. When an entity was removed, Movement Manager still had its own copy and kept moving it. Now, it returns the internal list directly. Both managers share the same reference, so changes reflects immediately. Next, we have generics on iMovement type. Before, the interface only accepted movable entity, forcing simulation strategies to cast to sim entity, which is unsafe unchecked cast. Now it's generic. iMovement type empty car movement declares same entity directly, so the compiler enforces the type. Let's move on to our design patterns, starting with strategy. iMovement type is the contract. Movement Manager calls move every frame and never knows the concrete type. Behavior is in the strategy, not the manager. Strategies can be swapped at runtime, meaning when the car is destroyed. On destroy sets a new strategy. Keyboard control is gone and the car calls under physics. No subclass, no flags. Next is proxy pattern. Empty car movement wraps empty movement statement. It adds keyboard force, but delegates zone management and physics sync to the inner strategy. Lastly, our solid and OOP principles implemented. OCP, new movement type, new class only. Movement Manager and movable entity never change. SRP, Movement Manager only calls move. Zone logic and input lives elsewhere. DIP, depends on iMovable entity, not concrete entity manager. ISP, empty car movement retrieves only iButton device. LSP, sim entity manager extends entity manager, both work identically. Abstraction, Movement Manager never knows what runs. Polymorphism, the right strategy executes automatically, no if else. Encapsulation, empty car movement privately owns its keyboard reference and state machine. Nothing outside breaks internals. Thank you.
I'm Jinhin 2500928. I'll now be talking about the input and output engine improvements. Starting with our biggest upgrade, how we retrieve hardware. In part 1, our manager just returned a generic device object. This meant our simulation classes had to manually guess and cast to things like keyboard or mouse, which is risky and can cause runtime crashes. To fix this, we implemented Java generics. Now the interface uses a generic type T, we pass in the class type we want, the manager safely casts it, and we get a strict compile time checking. No more bad casts. For mouse interaction, we had a bug where dragging an object too fast would drop it, or dragging it across another object would pick both up. We fixed this by adding a static last drag variable in the CR mouse response to act as a target lock. Now if you're already holding onto something, the code will ignore everything else. You can move the mouse as fast as you want and it stays perfectly locked onto just one entity. Moving on to design patterns, we use the flyweight pattern for our sound dev class. Instead of loading duplicate audio files every time multiple bombs explode, we cache the sound in a hash map so they all share the exact same instance in memory. Finally, for solid principles, we focus on the interface segregation principle. Instead of one massive input interface, we split it into highly specific contracts, like iPause device for the mouse and iButton device for the keyboard. This keeps our dependencies clean, ensuring clients only rely on the exact inputs they actually use.
Hello, my name is Kalnesh, and for my part, I mainly focus on the collision architecture of our project. The first key improvement was on-click collision detection. In part 1, the mouse query area was very small, so collision-based selection could be inaccurate, especially when trying to click objects precisely. In the completed version, on-click detection was improved by adding a larger padded query area. This makes collision detection around the cursor much more reliable. It also better supports stable object interaction during collision-based selection. The second improvement was in the collision response interface. In part 1, collision responses only accepted a general entity type. In the full version, the interface was improved using generics, so collision behavior can now work with more specific entity types while still following the same abstract framework. This makes the collision system more flexible and easier to extend. Now, for the design pattern, the main one used here is the strategy pattern. Collision detection and collision response are separated. The engine handles detecting when collisions happen, while the actual response logic is plugged in through identity collision response. This means new collision behaviors can be added without changing the detection system itself. In terms of OOP and solid principles, this shows single responsibility, because detection and response are handled separately. It also shows open-close principle, because you can introduce new collision responses by adding new implementations instead of modifying the whole pipeline. There is also dependency inversion, since the collision manager works with abstractions instead of being tightly coupled to one concrete response or detector. Overall, the collision flow is the engine detects a collision event, passes it through the collision framework, and then the assigned collision response decides what behavior should happen. So overall, the collision system became more accurate, more reusable, and easier to extend.
Hello everyone, I'm Fitris Daniali and my student ID is 2501344. So my portion of the project is the scenes system, basically everything the player sees and interacts with. In part 1, we had one scene. It worked, but it was more of a tech demo than an actual game because we were showcasing our abstract engine. But for part 2, we built 4 proper simulation scenes. Scene plane is our blank box at the bottom left there, you can see. You drag in whatever you want and you just blow things up freely. Scene preset comes preloaded with a specific arrangement of bombs, a car, trees, and a few rocks. So there's actually something to destroy from the start. Both scenes are fully self-contained. Each one has its own physics world, camera, and all of its corresponding managers. So there's a zero bleed between them. Then we have our overlay scenes, scene pause and scene instructions. Both of them hold a reference to the previous scene and call its render method first before drawing anything, which is why you can see the frozen game behind the UI at the bottom right when you pause the game. The dark theme is actually a 1x1 white pixel texture stretched to full screen at, I believe, around 70% opacity. So simple trick, but it looks quite clean. Yeah. So then next slide. So for our design patterns, the stack is literally our state machine. No enums, no switch statements. You just push, pop, and boom, you're done. Pause overlays, resume removes it, and switching scenes calls clear keep top, so nothing actually leaks. The stack handles all of it. Second pattern is a composite rendering. The engine only calls render on whatever's at the top, but scene pause quietly calls the game renders first. Then draws its UI at the top. Yeah. So 2 scenes, 1 frame. Engine has no clue, but sneaky, but it actually works. Solid wise, all 4 scenes talk to iScene control, never the concrete scene manager. So DIP is covered. We added all 4 scenes without touching the engine once, so that's OCP in action. And each scene has one job. Game scenes do physics, pause does the menu, instruction does the startup screen. So everyone minds their own business. Yeah. Thank you.